Welcome to This Explainer. Today, we're taking a really enthusiastic top-down journey straight into the very heart of your computer. We're going to trace the invisible, lightning-fast path of a simple mouse click all the way down to the raw hardware. So, think about it for a second. What really happens when you double-click an application, like a heavy game or your web browser? You see a window pop up almost instantly. But beneath that surface, in literally just a fraction of a second, there is an immense, insanely complex symphony of software and hardware coordination taking place. So who's actually conducting that symphony? Well, that conductor is your operating system. The OS is the ultimate manager, translator, and traffic cop of the computing world. It takes these high-level software commands, something like open this file, and translates them into the highly specific electrical signals that your physical hardware can actually understand. Without it, your software and your hardware wouldn't even know how to begin talking to each other. Okay, let's dive into this. To make sense of it all, we're going to follow a clear 6-stage map down to the silicon. We'll cover the hardware manager, user versus kernel mode, CPU scheduling, memory and RAM, file systems, and finally, device drivers. Stage 1. The ultimate hardware manager. Starting at the surface. We're going to begin our descent right where you live, the graphical user interface, or GUI. When you're clicking around your desktop, you're actually interacting with specialized managers. For example, in Windows, you have the Desktop Window Manager, or DWM, handling everything you see on screen. Think of it as a strict budget manager for your video memory. Whether you're firing up a heavy 3D game or just resizing a desktop image, the DWM draws all those objects, holds them in a buffer, and makes sure different applications are sharing the graphics processing unit smoothly. Actually, it's the exact reason a frozen app doesn't immediately corrupt your entire display. Stage 2. User mode versus kernel mode. Crossing the restricted bridge. As we go a bit deeper, we hit a massive security boundary. You see, the operating system splits your computing environment into two very distinct worlds. First, there's user mode. This is where your everyday applications, like your web browser, live. It's safe, but it has highly restricted access to hardware. If an app crashes here, it only kills itself. No big deal. But beneath that, that's kernel mode. This is the privileged core of the OS with totally unrestricted hardware access. The stakes here are incredibly high. A crash in kernel mode doesn't just kill an app, it brings down the whole ship, triggering a system-wide crash, like the infamous blue screen of death on Windows or a kernel panic on Linux. And this brilliantly illustrates why we absolutely need a safe bridge between these two worlds. That bridge is built on system calls and interrupts. Let's say your user mode browser needs to download an image. It can't just reach out and touch the Wi-Fi card directly, no way. It has to make a system call, which is basically a formal request to the kernel. On the flip side, hardware can send interrupts to the CPU, waving its hand to get immediate attention. When that happens, the CPU saves its current state, safely switches into kernel mode, handles the privileged task, and hands the result right back to the user app. Stage 3. Scheduling the CPU, the fair parent. Now we're down at the processor level, where the OS basically dictates time itself. When you're multitasking, say streaming a podcast while typing up a document, the CPU isn't necessarily doing both things at the exact same microsecond. Instead, the OS acts like a very fair parent. It rapidly switches processor execution cycles between those processes. It grabs the first process, saves its registers and stacks, loads up the second process, lets it run for just a fraction of a second, and then swaps them again. This happens thousands of times a second, which gives us that flawless illusion of simultaneous multitasking. To manage this crazy juggling act, the OS relies on some specific CPU scheduling algorithms. First come, first served is super simple, but you guessed it, can cause a massive holdup if one task is huge. Shortest job next minimizes waiting time, but it requires the system to know task lengths in advance, which isn't always possible. Then we have round robin, which is incredibly popular. It gives a fixed time slice, or quantum, to each process, ensuring no long task holds up the line. And finally, priority scheduling just makes sure your absolutely vital system tasks always run before any low-level background stuff. Let's move to step 4 and see how this builds. Managing memory and RAM, the juggling act. So, CPU logical addresses have to be mapped to physical addresses in your RAM. But what happens if you go crazy, open 50 browser tabs, and just completely run out of physical RAM? Well, the OS taps into virtual memory. It takes data you aren't actively using right this second and swaps it out to your secondary storage, like your SSD, just to free up space. But, word of warning, if you overload the system, it'll start spending all its CPU cycles just swapping data back and forth instead of doing actual work. That's a severe performance bottleneck we call thrashing. Now, exactly how memory is managed depends entirely on the system's architecture. It's fascinating because we can see distinct engineering approaches to the exact same universal problem. Windows, for instance, utilizes a mix of paging and logical segmentation. Linux leans heavily on fixed-sized paging with some really advanced virtual memory features. And then macOS employs similar paging mechanisms, but it throws in these cool on-the-fly memory compression techniques. They're all solving the same problem of translating logical to physical addresses, just in their own unique ways.
Down to part 5, file systems and storage, organizing the chaos.
All right, we've talked about temporary memory, so let's shift gears to permanent data on your solid-state drive. Now, what's really interesting about this layered pipeline is how we can trace a file request perfectly down the chain. When you click Save, your application talks to the logical file system. That passes the data to the file organization module, down to the basic file system, pushing through I/O control until it finally hits the physical devices. And here is how that flow actually protects your data. First up, the file organization module translates your abstract logical blocks into physical blocks on the SSD. But before it permanently updates the file system structures, it writes that transaction to a sequential log. Why? Because if your computer suddenly loses power mid-save, the OS can just read that log when it reboots and finish the job. It's a brilliant little safety net that ensures fast recovery and keeps your files safe from sudden catastrophic corruption. Finally, we've hit step 6, drivers, talking to hardware. We have finally reached the bottom layer. This is the direct interface with the physical hardware itself. A device driver is the ultimate translator. The operating system kernel is incredibly smart, for sure, but there's no way it can inherently know the specific electrical behaviors of the thousands of different printers, GPUs, and random USB peripherals out there. So the driver sits right between the OS and the hardware. It takes a totally generic command like print this page and physically turns it into the exact laser pulses or motor spins that your specific printer model requires. So the crucial point is following this exact sequence to see how this conversation actually plays out. It always follows a discrete 5-phase flow. First is enumeration. The OS detects the hardware and identifies it. Second, loading. The driver binary gets pulled into memory. Third, initialization. The driver claims its hardware resources. Fourth is I/O request processing, where the driver takes the software's request and actually executes it on the hardware. And finally, interrupt handling. The hardware signals the CPU to basically say, hey, the job is done. Just look at this incredible journey we've just taken. From the very moment you click an app on your GUI, you're firing off system calls that safely cross the bridge into kernel space. Down there, the CPU schedulers are dictating time, the memory managers are juggling your RAM, the file system is organizing your storage, and the device drivers are rapidly translating everything into raw electrical signals on the physical hardware. And all of this, it happens seamlessly, literally in the blink of an eye. Which leaves us with this final thought. You hold unbelievable processing power on your desk or even just in your pocket, but without the operating system constantly working as that tireless manager, translator, and protector billions of times a day, is your computer actually anything more than just a useless piece of expensive silicon? It's the software that breathes life into the machine. Thanks so much for joining me on this explainer, and keep questioning how the invisible world around you really works.